Power factor correction systems are used to improve the efficiency of electrical systems by reducing the amount of reactive power. When selecting and installing a power factor correction system, it's essential to consider the potential for load imbalance and how it might affect the system's performance. A potential issue arises when capacitors are added to all phases based on the power factor measured on only one phase. This approach can lead to overcorrection, particularly when dealing with unbalanced loads. An unbalanced load occurs when the current draw on each of the three phases is not equal. If the power factor is corrected based on the phase with the lowest power factor, the other phases may end up being overcorrected, leading to a leading power factor. Overcorrection can cause several problems, including increased voltage distortion, harmonic resonance, and reduced system efficiency. One method to address this risk is to install power factor correction capacitors on each phase individually. This ensures that each phase is corrected independently, maintaining a consistent power factor across all phases regardless of load imbalance. This approach provides a more accurate and balanced correction, preventing overcorrection on lightly loaded phases. Another option is to utilize a power factor correction system that monitors all three phases. These systems dynamically switch capacitors on and off as needed to maintain the desired power factor across all phases. By monitoring all three phases, the system can compensate for imbalances and avoid overcorrection. While these systems are generally more expensive than single-phase monitoring systems, they offer better performance and protection against potential issues caused by load imbalance. To determine the best power factor correction solution, consulting with a qualified electrical engineer is highly recommended. An electrical engineer can assess the specific load profile, analyze the degree of load imbalance, and recommend the most appropriate solution for a particular situation. They will take into account factors such as the type of load, the amount of load imbalance, and the desired power factor to select the right type and size of capacitors. In addition to choosing the right type of system, proper installation and maintenance are crucial for optimal performance. Firstly, ensure that the power factor correction system is installed by a qualified electrician according to the manufacturer's instructions and all applicable electrical codes. Secondly, regularly inspect the capacitors for signs of damage or wear and tear, and replace them as needed. Thirdly, monitor the system's performance to ensure that it is operating as intended, and make adjustments as necessary to maintain the desired power factor. Considering these factors, the selection and implementation of a power factor correction system can significantly improve electrical system efficiency and reliability while avoiding potential problems associated with load imbalance. Always prioritize a comprehensive assessment and professional guidance to achieve the best results. Power factor is the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amperes. It is a measure of how effectively electrical power is being used. A power factor of 1.0 or unity indicates that all the power supplied is being used effectively. A power factor less than 1.0 indicates that some of the power is being wasted. This wasted power is called reactive power, and it is caused by inductive loads such as motors, transformers, and fluorescent lighting. Reactive power does not perform any useful work, but it does increase the amount of current flowing through the electrical system. This increased current can lead to several problems, including increased energy costs, overheating of equipment, and reduced system capacity. Power factor correction involves adding capacitors to the electrical system to offset the effects of inductive loads. Capacitors store electrical energy and release it back into the system, which reduces the amount of reactive power. By reducing the amount of reactive power, power factor correction can improve the power factor, reduce energy costs, and improve system performance. Power factor correction is particularly important for facilities with large inductive loads, such as manufacturing plants, hospitals, and office buildings. These facilities can save a significant amount of money on their energy bills by implementing power factor correction. There are several different types of power factor correction systems available, each with its own advantages and disadvantages. The most common types of power factor correction systems are fixed capacitor banks, switched capacitor banks, and active power factor correction. Fixed capacitor banks are the simplest type of power factor correction system. They consist of a fixed number of capacitors that are connected to the electrical system. Fixed capacitor banks are relatively inexpensive and easy to install, but they are not very flexible. They can only correct the power factor at a specific load level. Switched capacitor banks are more flexible than fixed capacitor banks. They consist of a number of capacitors that can be switched on and off as needed to correct the power factor at different load levels. Switched capacitor banks are more expensive than fixed capacitor banks, but they provide better performance and flexibility. Active power factor correction is the most advanced type of power factor correction system. It uses electronic components to actively control the power factor. Active power factor correction systems are the most expensive type of power factor correction system, but they provide the best performance and flexibility. They can correct the power factor over a wide range of load levels and can also compensate for harmonic distortion. Harmonics are unwanted electrical frequencies that can cause problems with electrical equipment. Harmonic distortion can be caused by nonlinear loads such as electronic devices and variable frequency drives. Active power factor correction systems can reduce harmonic distortion, which can improve the performance and reliability of electrical equipment. When selecting a power factor correction system, it is important to consider the specific needs of the facility. Factors to consider include the size of the facility, the type of load, the amount of load imbalance, and the desired power factor. It is also important to consult with a qualified electrical engineer to ensure that the power factor correction system is properly designed and installed. Power factor correction is a proven technology that can save facilities a significant amount of money on their energy bills. By reducing the amount of reactive power, power factor correction can improve the power factor, reduce energy costs, and improve system performance. Power factor is defined as the cosine of the angle between voltage and current in an alternating current circuit. It represents the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amperes. A power factor of 1 indicates perfect efficiency, meaning all the supplied power is used for doing work. A power factor less than 1 indicates that a portion of the supplied power is not being used effectively and is circulating in the system as reactive power. Reactive power is caused by inductive loads like motors, transformers, and inductors, and capacitive loads like capacitors and long cables. Inductive loads cause the current to lag behind the voltage, while capacitive loads cause the current to lead the voltage. This phase difference between voltage and current reduces the power factor. A low power factor leads to several problems, including increased current flow in the system, high energy losses in transmission and distribution, voltage drops, and reduced capacity of electrical equipment. To improve power factor correction techniques are employed. These techniques primarily involve adding capacitors to the electrical system to compensate for the reactive power caused by inductive loads. Capacitors generate reactive power that is opposite in phase to the reactive power generated by inductive loads, effectively cancelling out a portion of the reactive power and bringing the power factor closer to 1. There are different types of power factor correction methods, including individual capacitor compensation, group capacitor compensation, and central capacitor compensation. Individual capacitor compensation involves placing capacitors directly at the inductive loads. This is the most effective method as it reduces current flow in the entire system from the load back to the source. Group capacitor compensation involves placing capacitors at load centers or distribution panels to compensate for a group of loads. This method is less effective than individual compensation, but is more cost-effective for systems with many small loads. Central capacitor compensation involves placing capacitors at the main incoming supply to compensate for the entire facility's load. This method is the least effective but the simplest to implement. Power factor correction systems can be fixed or automatic. Fixed power factor correction systems use a fixed amount of capacitance to compensate for the reactive power. These systems are suitable for loads that remain relatively constant. Automatic power factor correction systems use a controller to automatically switch capacitors in and out of the circuit to maintain a desired power factor. These systems are suitable for loads that vary significantly over time. When selecting a power factor correction system, several factors need to be considered, including the load profile, the desired power factor, the system voltage, and the harmonic content. The load profile is the pattern of electrical demand over time. The desired power factor is the target power factor that the system should maintain. The system voltage is the voltage at which the power factor correction system will operate. The harmonic content is the amount of harmonic distortion in the electrical system. Harmonics are unwanted frequencies in the electrical system that can cause problems with equipment and reduce the effectiveness of power factor correction. Power factor correction capacitors should be installed as close as possible to the inductive loads to minimize current flow and losses in the system. The size of the capacitors should be carefully selected to avoid overcorrection or undercorrection. Overcorrection can lead to voltage rise and harmonic amplification, while undercorrection will not achieve the desired power factor improvement. Power factor correction systems should be regularly inspected and maintained to ensure proper operation. Capacitors can degrade over time and may need to be replaced. The controller and switching components should also be checked for proper operation. Power factor correction is an essential aspect of electrical system design and operation. By improving power factor, energy efficiency can be increased, costs can be reduced, and equipment performance can be improved. It is important to carefully consider the specific needs of each application and to select the appropriate power factor correction system to achieve the desired results. Understanding power factor is crucial for optimizing electrical systems. Power factor, represented as a value between 0 and 1, indicates how effectively electrical power is being used. A power factor of 1, also known as unity power factor, signifies that all the supplied power is being used to perform useful work. A power factor less than 1 means that a portion of the power is not being used effectively and is circulating in the system. This circulating power is called reactive power. Reactive power arises due to inductive loads such as motors, transformers, and fluorescent lighting ballasts, as well as capacitive loads such as capacitors and long cables. Inductive loads cause the current to lag behind a voltage, while capacitive loads cause the current to lead the voltage. This phase difference between the voltage and current reduces the power factor. A low power factor results in several undesirable consequences. Firstly, it increases the current flowing through the electrical system. Since the real power remains the same, a lower power factor means a higher apparent power, which translates to higher current. This increased current can overload electrical equipment, such as transformers, cables, and switchgear, leading to premature failure. Secondly, a low power factor increases energy losses in the electrical system. The higher current flowing through the system causes more heat to be dissipated in conductors, resulting in increased energy losses. Thirdly, a low power factor can cause voltage drops in the electrical system. The increased current flowing through the system causes a larger voltage drop across the impedance of the conductors, which can lead to reduced voltage at the load. This can affect the performance of equipment that is sensitive to voltage variation. Power factor correction aims to improve the power factor by reducing the amount of reactive power in the system. This is typically achieved by adding capacitors to the electrical system. Capacitors generate reactive power that is opposite in phase to the reactive power generated by inductive loads. By connecting capacitors to the electrical system, the reactive power generated by the capacitors cancels out a portion of the reactive power generated by the inductive loads, thereby improving the power factor. The amount of capacitance required to correct the power factor depends on the amount of inductive load and the desired power factor. The higher the inductive load and the higher the desired power factor, the more capacitance is required. Power factor correction can be implemented in several ways. One method is to install individual capacitors at each inductive load. This is the most effective method, as it reduces the current flowing through the entire electrical system. However, it can be costly and impractical for systems with many small loads. Another method is to install capacitor banks at distribution panels or substation. This is a more cost-effective method for systems with many loads. However, It is less effective than individual capacitor correction, as the current flowing through the feeders and branch circuits is not reduced. Power factor correction can also be achieved using active power factor correction devices. These devices use electronic components to actively control the power factor. Active power factor correction devices are more expensive than capacitors, but they can provide better performance and flexibility. They can also compensate for harmonic distortion, which can improve the power quality of the electrical system. When selecting a power factor correction method, it is important to consider the specific needs of the application. Factors to consider include the load characteristics, the desired power factor, the cost of the equipment, and the maintenance requirement. Power factor correction is an important aspect of electrical system design. By improving the power factor, energy efficiency can be increased, costs can be reduced, and equipment performance can be improved. Power factor is a crucial concept in electrical engineering that significantly impacts the efficiency and reliability of electrical systems. It's essential to understand its implications and implement appropriate correction methods when necessary.